welcome to my presentation. In this talk, I will present a tool called VSPMiner, and we try to detect the security hazards in SEAndroid vendor customizations via machine learning techniques. This is who am I? My name is Xiangyu Liu, a security engineer at Alibaba Group. I earned my PhD degree from CHK in 2016. I have published several papers in both academic and industry, such as IEEE, SMCCS, and also DEFCON. Now my interests focus on applying AI techniques to solve problems in cybersecurity, especially like the intrusion detection, and I'm also very interested in mobile security. This work is also cooperated with Zhang and Yang also from Alibaba Group. This is an outline of my work. I will first present some background information, and also I will talk about the detailed techniques about this tool, and also following the evaluation and the summary. And as we know, to enhance the security of Android, after Android 4.4, Android use SELinux to enforce mandatory access control over all processes in Android system. As a result, privilege escalation becomes much more harder. And as reported in the previous works, multiple vulnerabilities have been prevented by the SELinux. Now I will introduce a simple framework about the SEAndroid. The SELinux LSM module located at the kernel space will be responsible for the resource access control, and it is supported by the security server located at the user space, and also the context information and also the policy information located at the user space. When the context information describes the details information such as the subject domain or the object types, and the policies define the strategies for the resource access control, and when the system boosting, the system server will load the policies into the SELinux LSM module and to complete a MAC access control. And the security server also can interact with itself or interact with the context information and also the LSM module through a enable SELinux. As the name of our presentation, we will focus on the policy part and try to detect the vulnerable policies designed by the third-party vendors. This is a policy language, and as we know, the effectiveness of the SEAndroid depends on the employed policies. And in general, there are two types of policies: annul and never annul rules. And for both rules, they have we refine the rules into 4 fields, and called in this presentation we will call it as a subject, object, and object class, and also permissions. And later, also the short names will be also used in my presentation. And the annul rules always define the benign operations, like allow app domain apps to read, write, or execute the app data files. And also, on the contrary, the never allow rules will define some privilege escalation operations. But this never allow rules is only used in the compile time, and after the compiling, there exists only the annul rules in the file SEAndroid. Like we can never allow such as untrusted app to read the very sensitive data, and after compiling, if we write some allow rules and maybe we write some wrong rules, right? So we can use the never allow to correct the mistakes we make. And the following is the security object, because such as the subject and object, it can map to the concrete subjects and objects, and such as the file context just as we see the context information describes the mappings, the relationship between the concrete subject or object between the labels. Such as a system file, it means that the files under the directory / system. As Linux introduced to Android, it seems everything goes well, right? But because Android is very complex, so Windows always don't know how to write policies, and this is a claim by a presentation at DEF-CON in 2013. So write policy is not an easy job. In practice, our strategy is first we will write some draft versions, and then we will try to refine the policies, and using the audit logs. And in general, the audit logs will contain 6 tuple access patterns, and in addition to the rules, it will also contain the concrete subject and the object. And policy engineers will pass these logs and to refine the policies. They will focus on the logs that are mismatched with the allowed rules. It means that some operations is not allowed in the defined by the policies, but it happens in real world. But such an approach is useful in practice, but it's very challenging due to many limitations, because we may have millions of audit logs in reality, and also the policy engineer maybe lack the expert experience, such as they don't know what's the blind access is, which is malicious, or the operations can lead to privilege escalation. And more importantly, they also cannot predict some unknown new malicious access patterns. This becomes more serious for the vendor customizations, because after Google release official version to different vendors, they will add some, such as add their apps or some drivers, also some new features. And it's also only a very small time window for the vendors to customize their official version. In general, it's less than 6 months. So in this work, we focus on the SEAndroid as the vulnerable policies caused by the vendor customizations. And this is a very urgent requirement. Okay, to address these problems, there are some previous works, and here I present a work have published in Usenik Security called SEAndroid. This work is complete by Samsung company, and they also only focus on their own devices, and they also use the audit logs, but they use semi-supervised machine learning techniques to expand the malicious access patterns. In their work, they only define a very small set of vulnerable access patterns. As you can see, that only 17 malicious access patterns they defined. They try to learn the unknown patterns based on the semantic correlations. First, they will use the near label classifier. This is very simple, right? So I will not explain. The second is pattern to rule distance measure. It will measure the similarity between the rules defined by the policy engineer and the malicious access patterns. And for the last one is co-occurrence learners. This is based on an observation that if an attack wanted to exploit some vulnerabilities, they will also contain a series of operations, and so they want to find the relationships in the series of operations. This is their main techniques. And different from the previous works, we present a new tool called VSPMiner. And as we see different from the previous works, there are some new features. First, we focus on all the third-party vendor images. And second, as we see that the EA SEAndroid only define a very small set of problem access patterns. And in our work, we try to extract thousands of vulnerable access patterns from the SEAndroid patch files. And also, we didn't rely on the audit logs. We try to extract the features directly from the malicious or the benign rules. And we also try to use the supervised machine learning. As we know, the supervised machine learning always have better performance than the semi-supervised or the unsupervised machine learning techniques. So the key idea in our paper is that we assume the latest AOSP policies is trusted, and we also define the rules have been deleted from the patch files as vulnerable. Here, you mean challenging me that the variable is not properly, but we want to see that if the if the rule is deleted from the SEAndroid, it must have some problems. It can help the policy developers to pay more attention on these rules. And at last, we also only focus on the critical rules, because maybe some rules only exist in one image, right? Because this is customized by one company. So we only focus on the critical rules. And what's critical rules we will define later. And this is a flow chart in our work. We first will extract many such as vulnerable rules and benign rules, and then use machine learning techniques to train models. And then we will extract the testing rules from third party and try to predict whether this customized rules is vulnerable or not. Now here is a detailed architecture of my work. We can see that we split it into three stages or into three parts. And the first is the training stage, and also the machine learning models, and also at last is the detection stage. For the training stage, our main task is to extract the vulnerable vulnerable rules and also the benign rules, and then we will perform the feature extraction. And after that, we will use the features to train different models, such as use several traditional or classical classifiers. And after that, we will try to acquire the testing rules from the different images and try to predict this, whether these testing rules is vulnerable or not. And later, I will show you the more detailed information and our techniques. First is that how to extract the vulnerable rules. And our strategy is to analyze SEAndroid patch files. As we know that the official website record the logs or the evolution of the SEAndroid. So we just git the logs into a log file, and we will obtain the commit IDs from the log files. So we can the end time in our work is August 1st last year, and we totally have nearly 10,000 commit IDs. And for each commit ID, we will diff it with its parents, and we will extract several. We will track such as added allow rules and deleted allow rules, and also the added never allow rules and also deleted never allow rules. For the diff content, we will further present differential analysis, and we will first focus on a specific commit ID, and focus on the allow rules. And because many operations and such as permissions and also the subjects may be combined together, so we first will we should split them separately like this way. And finally, each rule only contains one subject and one permission. This is very more convenient for us to perform the differential analysis. So after this, we can, for each commit ID, we can get a set of rules, such as deleted or no rules, and we will define it as S-minus AR ID, and also we can get the edit or no rules. So the differential analysis is performed like this way. We will use the deleted or no rules minus the added or no rules. Such as the result, we can see that init kernel security node policies. This will be appear in the final differential analysis differential result for a specific commit ID. And similarly, we will perform a very similar approach on the never allow rules, and we can get the deleted or never allow rules and also the added or no rules. But different from the allow rules, we will use the added never allow rules to minus deleted never allow rules. It's very easy to understand, right? So the final result, we can, for example, we can get the untrusted app to read init files. This will appear in the never allow rules. So finally, we can get two parts, right? And we want to combine all together. So we use this formula this equation to combine the results of all the commit IDs together. And finally, we can get PR prime. This is the result of all the commit IDs. However, there is some special symbols in some rules, because such as the stars and the dash and also the VV line, because they have different meanings. So we should handle these special symbols. Like the stars can match an item in the same field, and also the dash is exception operation, and it will perform on the subject and also the object. And the VV9 also refer to the except operations and is used in the permission. So to handle these special symbols, our strategy is to transfer them into concrete rules. So we define some critical field such as 4 fields like subject, object, and like this way. And so the critical field is defined as that has appears in the PR prime. So because in the common rules, that's of the PR prime. And so as a result, we can get several sets that describe all the different critical field information. So after we get this critical set, we can replace such as the stars and the dash and the VB9. For stars, we will replace it by all the corresponding critical fields. And also for the dash, we will replace it by all the other critical subjects or the operation or the object, and like this way. And finally, we will get PR. This is we can define it as known vulnerable rules. Different from the we get the vulnerable rules. The benign rules we obtain it to use a very simple approach. We just acquire the latest AOSP and SEAndroid, and we also only consider the critical rules, and we define these rules as R benign. So after we obtain these two sets, we want to construct the training set. But we also need to animate the inferences during the data processing, right? You can see that we have a very long chain of the data processing. So maybe we will make mistakes, or some logs also make mistakes. So we use approach to animate such inference. We will remove the intersection of the PR and R-benign, remove it from the both PR and R-benign set. So finally, we will get about 25,000 vulnerable rules, and it will be taken as the positive samples. And on the contrary, we will also get 24,000 benign rules, and it will taken as the negative samples. Based on the training set, we will try to do the feature extractions. Naturally, we will want to use one code encoding for each field. But after primary investigation, we found that it's not enough because it cannot because such features lack in-depth understanding by the such as expert, also the attackers, because some rules, which rule is more critical, cannot be explained by the features. So we try to assign weight information to the rules and make it better to explain whether the rule is vulnerable or not. Such weight information we acquire from both the vulnerable rules and also large-scale rules we acquired in later, and we will explain it later. So this is the weight information from the vulnerable rules. And in fact, it's just some frequency information, like the count information of each field in the vulnerable rules for each field. And we also take the count of the combinations. And here we only consider the object and the permission, because what operations can perform on object is very important when we judge whether a rule is vulnerable or not. So we take it out to as a weight information. And for all the frequency information, we will do a normalization, and finally we will get the different weight information about the different field and all the combinations. And similarly, we will also perform we will also extract the information from the large-scale rules, and we will also count. We will also do a static analysis on the count information of each field in all distinct rules. Maybe we have millions of distinct rules. Such as we also focus on the for field. This means that for the subject, if it appears in many rules, it means that the subject is very important and it has the ability to access many resources. So the weight information will be much higher than some other domains. Also, we will calculate the count of different rules in all images, because we have thousands of images, and if one rule appears in all the images, maybe the weight is maybe it's benign, maybe it's more preferred to benign, right? Because many companies want to design this rule. So we add. So finally, we will also do the normalization, so we can get weight information based on large-scale rules. After we finally we have get very complete features for the for us to do the further model training, and we propose several basic approaches to classify these features, like the random forest and also GDBT or SVM naive Bayes or KN logistic regression, like this way. But during the model training, we should note that there is some null values it will appear for the object permission weight and also the rule frequency, because it may not appear in the training set. But this is very, very small. So we replace these values. We replace the null values with mean values. It means that we will didn't assign any bias for the values for the weight information. For different models, we will do a cross-validation, and we will split the training set into two parts. And the 80% will taken as the training set, and the rest data will taken as the validation set. And we will also use the key criteria to judge whether the model or the algorithm is reasonable. And such as the criteria contains recall, F1 score, AUC, and also KS values. This is very classical criteria in machine learning techniques. So this is the result of the cross-validation, and we can see that GDBT, XGBoost, or the random forest have the significant better results than other linear classifiers. I think because the rules is also a tree-based access control, because you can see that the subject can access the object or like this way. So the tree-based classifiers always have better performance here. So in our experiments, we only use the three classifiers in our final models. After we training the models, we will talk about how we can acquire large-scale rules. In fact, we can clone different images from the Windows and also from other platforms, and then we can pass these images to get the different SEAndroid policies. But this is very hard now, because many Windows didn't allow users to download the images, and it's also a very tedious work or a very heavy task for us to complete this. So we acquire this data use app developed by Alibaba Security. It's called Qiandun. And this the rules are acquired anonymous, and also after the user agreeing, we can acquire this data. And also this is also followed by the Alibaba requirements. So after we can see that we will acquire the information, seven tuples, like the brand model and version, and also the following is the rule information. And we also connect the file context information, like because with the help of this file context, we can map the object to the concrete objects. And this is will be used in the vulnerable rules analysis. This is after we connect a large-scale data from the end users. We can filter out. We can connect only 22 mainstream windows, and also you can see the others also contains several other brands. And finally, we can get 22 brands and also more than 2,000 different images. Here, the different image means that the different tuple information, brand model, and version. And for each brand model and version, we will only select one image, because some images may be root from by some attackers or some malicious guys, right? So we will select the image with least rules as the last one, and we will combine all the rules together, and get about 5 million different rules, and this is also used in the training stage the features, we can extract the weight information from these large-scale distinct rules. After this, we will do the data filtering. Because we can acquire, you can see that we acquire a large scale of data. And first, we will remove the rules belong to Google. But this is also used when we assign weight information to the features. And after we remove the rules belong to Google, we also will select the critical rules from the vendor customizations. And after that, we will also detect whether these rules belong to the known vulnerable rules, because these have been detected in the training stage. And finally, we will get a large scale of testing rules. These rules don't belong to the known vulnerable rules. And for the rules that belong to known vulnerable rules, we will do a further investigation later. And after that, we will do a prediction process. And the models are used separately. And different from the approach used in SEAndroid, we use a more conservative approach, because only the rule is predicted as vulnerable in all the three models. We will label it as vulnerable. And finally, we get also many vulnerable rules, and also such as we can more than 2,000 problem access patterns are first reviewed, and later we will do a more statistical analysis and also analysis on these vulnerable rules. First, you can see that we do a statistical analysis on the rules based on the brand. You can see that let me see, the Lico, Nubia, and the OnePlus the situation is very serious. You can see that their percent is near or beyond 70%. And also, on the contrary, some companies also work much better in these areas, such as the Coolpad or Huawei, and also the Qikoo. They work much better in this area. And also, after this, we also evaluate the vulnerable rules based on the problem access patterns. The problem access patterns is defined by the object and permission. And we will also transfer this object into concrete subject based on the file context information we acquire from the end users. Like, we will transfer the app data file, such object will transfer to /data, right? So we can see that in practice, many attackers when they complete the privilege escalation, they will exploit the files located in the /data and the /system files. And here we also do a statistical analysis based on the process, because in the previous we focus on the file type, right? And then we can focus on the process. And this is, as reported in the SEAndroid, they report that such as the transition and the die transition process, two types of problem access patterns. And we can see that our VSPMiner also have a better result. They are also rank number 1 and number 2 in our results. And as we can see, we will also extend many other malicious access patterns in our work. And we can see that there is a very typical exploit patterns that the XGBoost. And this rule will make the attackers much more easier to complete the privilege escalation. And next, we will also focus on the capability. This is also, we will also compare our results with the SEAndroid. You can see that the SEAndroid reports 6 tuples or 6 types of problem access patterns, and such as kill, sysadmin, kill and sysadmin, and also sysptrace, and also other types. You can see that all these types of vulnerable access patterns also appear in our results. And we also, obviously, you can see we also extend more problem access patterns by the VSPMiner. And after that, we also focus on the devices, because in Android or Linux-based system, drivers is the most vulnerable component, and many privilege escalation is based on the vulnerability in the drivers. You can see that first, here we just show some examples, such as the logd can execute or mountain the ION devices. It's not reasonable, right? And for the GPU device, it means that such as the shell app and the same server can execute the GPU devices. And more importantly, that the app domain or the health D and some untrusted app can also write information to the input devices. This is also predicted by our by VSPMiner. And at last, you can see that some very common subject like the app domain or the shell can also get some maybe can have the ability to get some sensitive information from the audio devices. This is just to show some examples that we have found in our predict files. Here we show a very simple example. Such rule can assist the privilege escalation because such as this rule is allow system server to execute the system data file, and with this rule, if we have the ability to control the system server, maybe you see this is very hard, but in reality, we really can complete such process by exploit such as many vulnerabilities have reported, like a dirty code. With the help of the rule, the exploit will be much more easier. If we don't have this rule, maybe we should inject the exploit into the memory of the system server process, and such exploit will become much more complex. This is just a case study, and here we summary 2 types of classical exploit patterns. And the first is the object is system file, and the permission is execute no trace. And the second is object is system data file, and the permission is execute. You can see that we have do a summary or do a statistical analysis on the 2 exploit patterns. For the first one, you can see that we also get very vulnerable rules like the untrusted app and also the shell domain. Even for the last one, no debug D to execute no trans for the system file is also very vulnerable, because in reality, if we can control the debug D, or we can also replace the debug D into some other subject domains, if we can execute this system file, and we can with this help, we can trigger other vulnerabilities, such as in reality, we rarely trigger a vulnerability in MTK stack overflow, and so this will help us to complete the privilege escalation. And for the system data file, and if we have the ability to execute it, it's also very vulnerable. You can see that we predict such as the shell and also the untrusted app and also the system server. We have explained in the previous. You can see that the shell and the untrusted app is more dangerous, right? So our work is also promising. After this, we can record the processes we have, the problem that we live, right? We try to detect whether these vulnerabilities belong to the known vulnerabilities. Here, our insight is that if the rule has been deleted from the LSP, but it may also exist in a newer vendor versions, this will reflect the SEAndroid ecosystem, and many vendors don't care about or don't follow the Google's LSP policies. And you can see that there is the worst case happens on such as Meitu and also Xiaomi and ZTE, these three companies. And you also can see that Chinese company Chiku did very well, and also you can see other companies. They follow the LSP much better than other companies. Here we also want to show an example. How can we leverage such situations to assist privilege escalation? Like this way, we have one rule, allow init to load policies. Such rule has been deleted before or start from Android 6.0. But we found it's also in our study, because our study maybe have a very long span. So we also found it also exists in Samsung S7 with Android natural greater or equal to Android 6.0. So with the help of this rule, we can very easily bypass the mandatory access control enforced by SE Linux, because we can load any rules we want to help the privilege escalation. Also here we want to summarize our work, and in this work we perform in-depth analysis on the state of art SEAndroid policy refining techniques, and also revealing their limitations. And then we present a new policy analysis tool, VSPMiner, and try to detect the vulnerabilities, vulnerable SEAndroid policies in the wild while machine learning techniques. And then I think the results as shown in the presentation, you can see that the results also suggest that our approach is very promising. And at last, we also present some showcases. These cases will help us to assist the privilege escalation in reality. And also, such problems is very serious in reality. And finally, thanks very much. And any questions, or we can, if we have some questions, we also can discuss offline. Okay.
Did you consider uploading any of your, so you can translate the problematic rules that you found into never allow rules?
Yeah.
Did you consider submitting any of those to the open source project?
You mean we consider never allow rules? What?
So your result was rules that you thought were vulnerable.
Yeah.
Did you consider submitting, so never allow rules assert that you cannot add allow rules?
Yeah.
So did you consider submitting any of those to the Android open source project?
Sorry, I didn't understand your last one. Last sentence.
Android is an open source project, so
yeah.
You can make submissions to it.
Yeah.
Did you consider submitting anything to it as a result of your work? Or could you submit to it as a result of your work?
它是在问，就是得出来的研究结果有一些按照没办法这些路，他们这些研究结果会不会考虑把这些研究结果分享到企业的这些
Okay, we can Oh, okay, okay. We can publish the results. In general, we want to also write a white paper or the paper and with the data source, and just the results, such as the vulnerable rules that have been designed by, developed by the companies. Yeah, we can release the rules.
Okay. Yeah. So when you submit Neverallow rules, the great open source project, they actually get run as part of the compatibility test suite. And so if you submit Neverallow rules there, then that will actually prevent the device manufacturers from adding those rules to their own policy. So you can actually prevent them from adding those vulnerable rules to submissions.
Okay, okay. Thanks very much. We will release this. Okay. Okay, if you have no question, we can stop my presentation, and thanks very much.